All right. So today, start. It is. All right. So today, what I want to talk about is the stuff we're starting to do. I think anyway, the stuff we're starting to do is starting to get a little bit tricky. Today, I want to do a couple of examples from 11.8 of computing convergence of radius of convergent power series, and then I'm going to talk about 11.9, which is working. I mean, it's called functions as power series or power series as functions. But really, it boils down into two subcategories, which is deriving new series from old ones, and couples with series. And then sort of above all of this, and the very, very, very first thing I want to do, if anybody has any, is I would like to answer any homework questions that anybody has for me. If there are any homework questions to be answered. So the floor is yours. Any questions I can deal with, administrative or not? Yep.
This isn't a homework question, but it's more so from last week's stuff. So for the comparison test, when we're proving if one function is less than another function, like you want us to do the algebraic.
So there's a couple of different ways. I mean, yeah. So if you're going to use the comparison test, I mean, so if it's obvious that something is smaller than something else, you can just say it. So like if you had something like 1 over n squared, you're certainly allowed to say something like that, right? 1 over n squared is smaller than 2 over n squared. Traditionally, it would be in your best interest to write down, if you have a statement like 1 over n plus 1 is less than 1 over n, it takes almost no time for you to prove this algebraically, so you should do so. So yeah, if you're going to use the comparison, make sure that you get this from someplace. That's true whenever this is, which is true. These are equivalent statements, right? So write down the thing you're trying to prove and then some sort of justification for why that's true. So justifications are important for me. I like to see justifications for inequality. Okay. But you don't need to be like verbose about it, right? Just whatever the minimum is that you think you need to do. The goal of all of this is for you to convince me that you understand what's happening. Right. So if you don't write something down on the page, I have no evidence of to support the idea that you understand what's going on. Even if I know you do, the only evidence I can work with is what's written on the paper. But you don't have to write an essay. Anything else? Okay. So let's start with some examples from 11.8 here. Just to example 1 from 11.8. I picked out a couple of questions from the homework questions from the book, because I think having more examples of how to work these things is important, especially because I noticed that the way that it's okay. Sorry. I noticed that the way that the WebAssign often asks these things is there's 2 boxes that say conversion or divergent. It doesn't actually, or you can just poke around and guess what the radius of convergence is. So I want to have a couple more work examples here. Historically, this is one of the hardest tests in calculus sequence. I'll make sure that everyone's getting the appropriate amount of practice. All right, there's a power series. And the way this question will be asked is find the radius and interval of convergence. Okay. Now, I guess to be totally correct, I should probably tell you what the indices are. So here we are. We're looking at a power series. What do we do? Ratio test, right? That's all we got. Ratio test, power series, ratio test. So hit this with a ratio test. Just being very careful to make sure that you get this algebra right in here, because if you don't, these problems can go really wrong. right? So you compute that limit. Carefully. What you're left with is 5x minus 4, because the n plus 1 on top and the n bottom cancel and leave one copy behind. And then there's an n plus 1 cubed down here. There's an n cubed up here. So when you're finished, you get that. I'm going to strongly encourage you at this point, when you do these limits, like I pointed out last time, when you're doing this, it's usually best practice to take whatever chunk has axis in it and just take it outside the limit so you don't accidentally destroy it. Or worse than that is, it's really easy in the heat of an exam when you're moving quickly to just plug n in for x as well, which usually destroys the questions. And so just as a best practice sort of thing, I like to pull whatever is left over there outside. Not really, the limit doesn't really apply to it. So when you're done computing this limit here is 1. And so you're left with the absolute value of 5x minus 4. Okay, so here's a question. What is the center of this series? I heard somebody whisper with
4/5.
why?
Is 5x minus 4 is 0.
Yeah, right. If you put in x is equal to 4/5, right here, what'll come out is 0, right? So the center of the series is the number that you plug into it that makes a list of zeros, right? So if you were looking at a series just from the very beginning, you should have known, or you could have suspected, well, this isn't in standard form, because it's not x minus a to the n, but I could put it into the form x minus a to the n. So if I was trying to put this in standard form, I might factor the 5 out. So I would get a 1/5 to the n times x minus 4/5 to the n over n to the third. That's a typical sort of move that happens in these types of exercises, right? If you don't understand quite what happened here, this is supposed to be a 5, yeah, 5. Pull the 5 out, factor out the 5, this is what's left behind, but that is still to the nth power, so the 5 has to keep the nth power on it. So the center of the series is 4/5. And you're going to get that information anyway when you solve this equation. When does the series converge? Series converges when the limit then goes to infinity, and plus an array is less than 1, which gives you this. Now, there's another common mistake that people make here, which is they say 1 is the radius of convergence, right? Because you've got a 1 right here in this inequality. The problem is this is not in standard form. Standard form for computing radius of convergence is x minus a is less than r, with no number attached to the x. Okay? So the radius of convergence for this problem is not 1 because every single limit test or ratio test is going to put a 1 right here. If you took this equation and as part of solving it, you put it into standard form, so that is you took the 5 off of the x, but you could divide everything by 5 and you're going to end up with this. So now that's in standard form because it looks like x minus a. X minus a is less than r. And remember, a is the center and r is the radius. So in this question, the radius of convergence is 1/5. And the center of the series is at 4/5. So where does the series converge? At least, well, it converges at least for values between a minus the radius of convergence and a plus the radius of convergence. This is a thing that shows up in the descriptions of these theorems. Or you can algebraically solve this. So this would tell you 4/5 minus 1/5 up to 4/5 plus 1/5, which is 3/5 up to 1. Or if you don't like remembering formulas, and I don't, I much prefer to just work with algebra, you can just finish solving this equation. The absolute value of x minus 4/5 is less than 1/5 happens whenever minus 1/5 less than x minus 4/5 less than 1/5. Add 4/5 everywhere and you get the same thing. So the more general way to do this is to remember that if you know the center and the radius, you can just write the interval down if it's in standard form, or you can just algebraically figure out what the big part of the interval of convergence is. Okay, same answer either way. Am I done? Why not? Test the endpoints. So what happens in this one? Well, I don't know why I just erased the series I'm working on. I have 5x minus 4 to the n over n to the third. Okay, so if I evaluate that at the endpoints, say we just put in 1. What I get is 5 minus 4 to the n over n to the third is 1 over n to the third. So if you're going to tell me something converges, make sure you tell me why. Why does that converge? P series. P series of P3. How about the other one? I do the same thing, but I do it at minus, not 1, at 3/5. You get 5 times 3/5 minus 4 to the n. So 5 times 3/5 is 3. 3 minus 4 is -1. So you end up with this. I get there be at least 2 good answers for why this converges. Certainly it converges by the alternating series test. Is there another thing I could say?
Absolute.
It's absolutely convergent because its absolute values are this series, right? The absolute value of this series is that one. That converges. So this also converges absolutely by P series. So this also converges. So when you're done, the interval of convergence, notice I have not written the interval of convergence anywhere until the end of the question because I want to make sure that I test my endpoints to make sure that my function is defined there is all of the points beginning with and including 3/5 and ending at and including 1. That's your interval of convergence. Okay, so I know these are long, but that's kind of the way this goes. Okay, let's see. Good. Oh, guess I set this up for my right. Okay, so I'm going to leave this behind for the rest of the class today. Are there any questions about how any of this technique works? It's pretty straightforward, I think, as long as you remember all the pieces of it. And remember, the hard part about it is that not only are there 3 things to check, you also have to make sure that you remember how the series tests work for individual series. Okay, let's talk about 11.9, which is where the real power of power series begins. This is chapter 9, which is about power series as functions. So we're going to explicitly think of power series as functions now. In the last section, we sort of played around with the idea that x was a variable and we could plug things into it. But now we're going to actually work with these things like they're functions, which means we're going to allow ourselves to compose them with other functions, for example. So here's right out the gate, I'm going to start with a theorem And the theorem is just that, I'm not even sure this one's in the book, that f of x is equal to the sum from n equals 0 to infinity of Cn x minus a to the n. If you have a power series, it's okay to think about it as a function you're plugging x into, as long as you are in the interval of convergence. Forget the endpoints. We're just going to talk about like that this is well defined as a function if the radius of convergence is positive. So that means there's not just one point that you plug in. And x minus a is less than r. So what we're saying is this function is totally, this expression, this is totally okay to think about as a function, as long as x comes from the interval a minus r to a plus r. And the reason we want r to be positive is so that's just not a single point. Kind of a stupid function if I can only plug one number into it. Okay. So basically, look, here's some jargony mathematical definition. You want the plain language version is power series are functions where they converge. That's the deal. If I have a power series and it converges, I can think of it as a function. If I can graph it, I might be able to differentiate it. Okay, so the big thing, the first thing, and Stewart doesn't actually say this, which is kind of weird because this is kind of a big idea, is if something is a function, you can compose it with other functions. Right? Remember that if I have f composed with g of x, what I mean is take f and everywhere I saw an x, put a g of x in its place. Right? This is function composition. So the first thing we're going to do is we're going to try to use power series we know to make new power series by using composition. So remember, the 1 over 1 minus x has that form, right? Sum of x to the n. And as a function, this is valid with these values of x. So this is a function. If I just name it f of x. Well, that means I can start putting other things in, because anytime I have a function, I could replace x with a function. That's what composition means. So I might think to myself, okay, well, what happens? Maybe I let a function g be equal to x squared. What happens if I take that function to f and I compose it with g? Well, f composed with g of x is the same as f of g. But f of x is 1 plus x squared plus x to the third. So this is just 1 plus g squared plus g to the third plus g to the fourth and so on. That's what composition does, right? I replace x with a function on g. But what's the rule for g? Well, it's x squared. So this is 1 plus x squared plus x squared squared plus x squared to the third plus x squared to the fourth, which I can think of as 1 plus x squared plus x to the fourth plus x to the sixth plus x to the eighth. So on the one hand, thinking about f as a power series lets me plug this other function into it, right, to get a new power series. But on the other hand, I have another way of writing down f and g of x based on this formula. F is also equal to 1 over 1 minus x. So f composed with g is also equal to 1 over 1 minus g. On the one hand, it's equal to this. On the other hand, it's equal to that. What is 1 over 1 minus g? It is 1 over 1 minus x squared. So the point of this is the fact I have two different ways of thinking of the same function means that I just got a power series for something that's not 1 over 1 minus x. But we just cooked up, without having to use Taylor series or any advanced methods, is that 1 over 1 minus x squared as a function can be written as 1 plus x squared plus x to the 4th plus x to the 6th, and so on. As long as g follows the same rules that applied to x. Whatever goes in this box has to have the property that that rule holds, or this formula doesn't make any sense, right? Whatever's in this box had better be between -1 and 1. Well, this is easy in the case of x squared because the absolute value of x squared is less than 1 whenever this is true. So the idea is I can't just compute a formula. I also have to check to see where that formula works. So replacing x with x squared gave us a new power series that has the same interval of convergence that we started with. So the point is, we can algebraically manipulate expressions that look like series we already know to get new series. In sigma notation, this looks like this. Okay. So now the slightly harder examples. The idea of this illustration is to show you that because we're thinking of this as a function, I can do composition. And if I know a formula for what this adds up to, the composition works in both versions. It works in the series version and the formula version. So here's a slightly more complicated example of the same idea. So example 1 from 11.9, which is find a power series or, I don't know, 1 over 1 plus 2x. So what I'm going to try to do is I'm trying to yank that apart into a composition. And the only thing that I know the power series of right now is this. This is our base tool, right? So if I could write this as a composition of two functions where one of the functions was that, I could use this series representation to come up with a series for this guy. So I need to make it look like 1 over 1 minus something. Because if I could find something to put in the box, I could write this as 1 plus whatever's in the box, plus whatever's in the box squared, plus whatever's in the box cubed, and so on, because I know a formula for 1 over 1 minus x. We'll go to the box. -2x. I need to have a minus sign right here, and the easiest way to do that is to rewrite this like that. 1 over 1 minus something. But now the something can go in the boxes. So, if there's a minus 2x here, I can put a minus 2x here, and a minus 2x here, and a minus 2x here, and so on. The fact that I've algebraically manipulated this thing into a composition means that I can write a series down. Now, this is already a power series, but it's going to be hard. I mean, it doesn't have the form of a power series yet because it doesn't look like coefficient times x to the n. So when I'm doing this, I have to make sure that I do enough algebraic simplification so it looks like a power series. Or if your math professor says it would be great if you put these in sigma notation, you should try to do so. And perhaps I will tell you, please put your series in sigma notation. Tell me right. So here's where we are. We have 1 over 1 minus -2x is the same as 1 plus -2x squared plus -2x to the third, which is 1 minus 2x plus 4x squared minus 8x to the third and so on. You don't have to multiply these things out if you don't like. What I'm noticing here is this looks like minus 1 to the n. And then there's some 2 to the n's running around. And there's an x to the n. If you don't like me having multiplied these things out like this because it actually makes it harder, you can go like this. Minus 2 to the first, x to the first, plus minus 2 to the second, x to the second, plus minus 2 to the third, x to the third. It's actually sometimes easier to figure out what the sigma notation is without simplifying the numbers out. Okay, now we could use the ratio test on this. We can use the ratio test on this to figure out radius of convergence. Power series don't mean anything without radius of convergence. But is there a faster way? What was the radius of convergence of this? What rule had to be true about x? This had better fall in the range of values between -1 and 1, right? Whatever's in the box had better fall between these values. And that means whatever I put into the box had better fall between those values. This will converge whenever -2x falls between -1 and 1. Whatever went into this machine has to satisfy the rules of the machine. Another way of writing this would have been this. So the answer is values of x have to fall between -1/2 and 1/2. Power series don't mean anything unless you tell me where they work. Radius of convergence or interval of convergence or whatever, this converges on the reason we're staying away from the endpoints is because eventually we're going to be doing calculus and we don't do derivatives at endpoints. Make sense? It's much faster to do this approach than to try to use the ratio test here, though you're welcome to, you get the same answer. Okay? We derive the interval of convergence from the conditions that existed on the original series. Okay? So now I'm going to motivate, I'm going to try anyway, to motivate what happens in cases where, I mean, so that you can imagine these get more sophisticated than this. You can imagine you had something like, you know, how would you deal with something like 1/2 minus 2 plus 3x, say? Lots of approaches to this. Yep.
After you get to the inequality ideas and everything, you have to check the bounds then?
So normally in a problem like this, you'll be asked to find the radius of convergence and not the interval of convergence. And if you're asked to find the radius, you don't have to check endpoints. Right. So I didn't do that because I was interested in what the radius of convergence was, which it explicitly does not allow the endpoints to be considered. So if you get asked for the interval, check the endpoints. If you're asked for the radius, you don't need to.
Okay.
Yeah, so here, this is a radius of convergence. Actually, let's this one. Let's do an example that I want to build up to. That's related to the one we did earlier, the 1/1 minus x squared. I've got 1/1 plus x squared. I guess your math professor radar should be going off here because 1/1 plus x squared is kind of a special function. We know anything about it? Like, where does this show up? In the land of calculus, specifically in land of calculus 2. This is, what about the inverse tangent? So inverse tangents are definitely involved. What's that?
I'm not sure.
That's the derivative.
It's the derivative of the inverse tangent, right? So 1/1 plus x squared is the derivative of the arctangent. Okay. So 1/1 plus x squared is the derivative of the arctangent. So maybe I have this idea that maybe if I could figure out how to do two things, I could come up with a power series for the arctangent. The first thing is I need to know a series for 1/1 plus x squared. That's pretty easy, right? The series for 1/1 plus x squared I can think of as being 1/1 minus x squared. So there's the thing that's going into the 1/1 minus x box this time. The fast way to do that is to write the sum of minus x squared to the n. You don't have to write out term by term. You can plug it straight into the sigma notation. And then if you're comfortable manipulating sigma notation, this is just the sum from n equals 0 to infinity of -1 to the n x to the 2n. Because, and also this, that better be less than 1 in absolute value, which means that the radius of convergence is 1. Right? Okay. Damn, I've almost got a power series for arctangent, because look, I've got a power series for its derivative. So what I know right now, I've got this. I have d by dx, but the arctangent of x is equal to 1/1 plus x squared, which as a function is equal to the sum from n equals 0 to infinity. That power series whenever that radius of convergence is satisfied. If only there was a way that I could figure out how to take that power series, which is the derivative of the arctangent, and turn it back into the arctangent. If only. So how do you want to do derivatives? Integrals. So we got to be able to integrate power series. Yeah. Yeah, it's a function. I can integrate it. And it's easy to integrate because they're polynomials, right? Power series of polynomials. Here's what we hope is true. Let's just suppose for a second. Let's pretend. Pretend it is legal to integrate a power series. What would that look like? Well, if you had a series f of x that looked like 1 plus x squared plus x to the third plus x to the fourth and so on, if we just imagine for a second that this was a giant polynomial, and I just slapped an integral on there, just imagining for a second that this infinite list of terms was really a polynomial, how would you integrate it? What if there was no dot, dot, dot there? What would you do? Gotta do something. Term by term, right? It's a polynomial. You integrate the 1, and then you integrate the x that I forgot. And then you integrate the 1, then you integrate the x, and then you integrate the x squared, then you integrate the x to the third. So what you would hope would be true is that power series can be integrated the same way. That if, and I'm going to lie to you slightly here, but you really hope, really more than anything, you hope what happens is that the integral can go inside and touch each term individually. So you really want it to be the case that this is true. Dot, dot, dot forever, and then I guess because it's an indefinite integral, you got to put plus c on it. Still a function, right? I mean, this is the only way that it makes sense that this math would ever be used by anybody anywhere is if this is true. If this really is like an infinite polynomial, I should be able to integrate each individual term. So it turns out to be the case, you can. As long as you are within the radius of convergence, this is a legal thing to do. So this integral really does turn out to be x plus x squared over 2 plus x to the third over 3 plus x to the fourth over 4. And then at the end, you got to put the plus c on. Now, mathematicians of good taste will not do this forever and then stick a plus c on the end. Instead, what they do is they write the c at the beginning. And the reason they do that is, one, so you don't lose track of the c, and two, because c has degree 0, so it makes sense to put it in the polynomial in the spot of b. So if this is true, man, this sure looks like all I did was apply the power rule an infinite number of times from the end of calculus 1. If I could do this, if I could integrate term by term, I could find a series for arctangent just by integrating this. That's what we do. Here's the theorem. The theorem says you can, here's the plain language version. You can do calculus on power series term by term within the radius of convergence. This thing we've suggested might be true actually is. And so really it is the case that power series are giant polynomials in this sense. Why should I ever have to integrate 1 over 1 plus x squared when I could just integrate it to polynomial instead? Maybe there's not even any such thing as the arctangent. Maybe all the arctangent is the integral of this power series. In fact, one of the more irritating things about differential equations when you get there is that many differential equations, which are the governing equations of all of science, do not have solutions that you can write down as nice things like arctangent. Instead, the solutions are these god-awful power series that solve the differential equations. The differential equations are like a core technique in solving differential equations, which are like the language of modern science. Because if the function doesn't have a form, there's no formula for it, you can still write a power series. So now I'm going to stop evangelizing power series for a second and actually show you how this integral works. So in this case, so we know that the derivative of the arctangent of x is equal to this power series. Minus 1 to the n, x to the 2n. So I can think of two ways to write this answer down. There's the sort of term by term way of writing it down, and then there's the sigma notation way of writing it down. Once I do the sigma notation way, I'll show you what it is in general. So the term by term way would be to write down that this is equal to 1 minus x squared plus x to the 4 minus x to the 6 plus x to the 8 and so on. That the derivative of arctangent is equal to this series. But that must mean that the arctangent is c plus the, it'll be the integral of this thing. After all, if the derivative of arctangent is this series, arctangent must be the integral of it. But it means to be an antiderivative. Then we just integrate term by term, and that means that the arctangent is equal to x minus x to the third over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9, and then somewhere out here there's a plus c. Of course, a mathematician of good taste would have written the c at the beginning. So it's in ascending order. And this is one answer. This power series right here, that's arctangent. Arctangent is not, yep. Did I mess something up?
No, I'm just I'm confused as to like how you got like just at the top. How do you get like the derivative of arctangent x is equal to that series?
Because remember, the derivative of the arctangent is 1 over 1 plus x squared. Well, 1 over 1 plus x squared is the same as 1 over 1 minus x squared.
Yeah.
And the series for 1 over 1 minus x squared is 1 plus minus x squared plus minus x squared squared plus minus x squared to the third, and so on. Because that's the series, that's the geometric series, right? 1 over 1 minus anything is the anything is 1 plus the anything squared plus the anything cubed and so on.
I see.
So the series, this series came out of this kind of substitution, where we're just using the series for 1 over 1 minus x. It's a very good question. It's easy to get lost in all the details that are going on here. Okay. Okay. So this series came from the observation that really right here, there's a 1 over 1 minus, there's a 1 over 1 plus x squared, which is equal to 1 over 1 minus x squared. Yeah, so all these little fiddly details going in the background, they give you the series. But then once you have it, you can integrate it. So in some sense, you could just say, there is no such thing as arctangent. What do you mean the inverse of tangent? No, there's only this very specially structured power series. That's it. It happens to be the case that it undoes tangent, but there was nothing special about the fact we named it arctangent. The series is what makes it fun. Okay. Oh, what's the radius of convergence? When is this valid? From -1 to 1, just like the original one. Yeah, it's still -1 to 1. Whatever's in this box has to satisfy this. And that will be true whenever that's true. So integrals and derivatives of power series inherit their radius of convergence. The formula is valid everywhere the original formula was. So basically, there's no point in learning any functions except power series, right? Because everything is a power series. So let's just do power series forever. Not totally true. Okay, so here's another classic along these lines. Oh, I guess let me give you actual theorem first. Here's what the theorem says. It describes the technique that we just did, where we took a series and we integrated it term by term to get a new series. Theorem says that if you have a power series and the radius of convergence R is positive, that is, we're not dealing with functions that have a single point, right? There's got to be some domain that's got some size to it. Then 1 d by dx of f of x is equal to, well, how do you take a derivative? What if I just wrote that down? What is its derivative? So this is the sigma notation way of doing this. If I just wrote down this form and said find the derivative, what would it be? Cn is a constant, n is the power. How do I take the derivative of that? Power rule, which would say? Drop the power by, pull the power out, drop the power by 1. Now it ends up going from 1 to infinity because whatever the constant term was destroyed by the derivative. Right? If there was a 1 in front, it's just gone. So the sigma notation version says, yeah, you just take the derivative of the formula for the term. If you can get comfortable with this sort of idea, it's usually faster to do it in the sigma notation than to write out the terms and do it there. But likewise, you could also write, if you want, C1, I mean, it's d by dx of C0 plus C1x plus C2x squared and so on, which is the C0 gets destroyed because the constant. You get a C1 and a 2C2x and a 3C3x squared. That formula and this formula are the same. So this is a giant polynomial. Treat it like a giant polynomial. Really what's going on in the background here is you have to say f is differentiable on a minus r to a plus r. So the derivative has the same domain the original function did. Basically, power series are awesome because they're giant polynomials. Polynomials you can take derivatives of as many times as you want. Okay. 2, the integral. I'm going to put 2 up here. Second part of the theorem says, what do you do when you integrate? Again, you're going to get a term by term version and a power rule version. 2 is integral. on a minus r to a plus r, and the integral of fx is equal to the, well, power series from n equals 0 to infinity. Now integrate that term. How do you integrate a term? Our rule says do what? Add 1 to the power. Divide by the new power, right? Cn over n plus 1 x minus a. 1 plus 1. So the integral of a power series is exactly the same as the power rule for calculus. So it's infinite applications of it. Or if you like, it's the integral of 1, sorry, C naught. Oh, I forgot something. Bad taste, put your C up in front. There you go, C plus. That's a nice ascending order. Or you can think of it as the integral of C naught plus C1x plus C2x squared plus C3x to the third, and so on, which turns into C naught x plus C1x squared over 2 plus C2x to the third over 3, and so on. So you can think about it as integrating the sigma notation once, or integrating the pattern from the power series. Okay. So once you've got calculus in the mix, these things get way more useful because you can do all kinds of things with them, right? In fact, you know, those of you that have already seen Taylor series probably thinking like, why would you ever do it this way when you could just use Taylor series instead? The answer is there's entire families of things where you may not even know they have derivatives or want to compute them. By the time you're 4 derivatives deep into a quotient, for example, you don't really want to do quotients anymore. So when we get there, again, I'm only selling this to people who've seen Taylor series who think this is useless, we can just use Taylor series. Go ahead and try to compute a Taylor series of 1 over 1 plus x squared to like the 5th term. Good luck. Because you'll be taking 5 derivatives of that thing. I'm not doing that. You can. So this is a fast way of doing it, and of getting new series from old series, and also a justification for why we even want to be able to do calculus on power series. So I will tell you, the last thing I'm going to say today is generally in higher level mathematics and modeling and engineering, the only object that gets worked with is some kind of power series. Eventually, the central object of differential equations you've never seen one before. Those are equations defined with derivatives. They're the core of physics and therefore at the core of everything else in the physical sciences. The central object of differential equations are power series. And there are some functions that have no other representation. So were you guys ever told, here's a point here. Were you ever told that about this guy? That has no antiderivative. That if somebody wrote that down, there's nothing you can do. There is no function in simple form that you can write down that has e to the x squared as a derivative. And that's too bad because e to the x squared is what gives you the normal curve, the bell curve from statistics, for example. Very important. But there's no antiderivative. But this thing comes up all the time in applications. So commonly it gets a name sometimes. The error function, it's a stupid name for it, but you know, they call it. So it has no antiderivative. So how do you work with something that's ubiquitous? It's all over math and science, but it has no antiderivative. And the answer is you replace it with its power series and you work with approximations. So what power series give you a way to do is to write the answers to problems down that don't have answers in closed form. E to the x squared, as we'll see, is just this. That's the power series for e to the x squared. But you can integrate this because the same rules apply. So the integral here is what is c plus the sum from n equals 0 to infinity of x to the 2n plus 1 over n factorial times 2n plus 1. Now, there's no function that has this power series that I can write down, but the power series is a function. This is the answer to this. So once you get power series, you greatly expand the library of problems you can solve, because you can solve things like this. All right, and we'll say in the next couple of lectures, we'll see why. We're going to do some more examples of calculus next time. And we'll see when we get to 1110, we'll see why this is the power series for EDX. All right. Keep it up. I know this is tough. I know. Are you going to have